within the past couple days, we actually found a really cool tool to help out in this class. And part of what I want you to do before our next lecture is kind of explore this a little bit. What this is a RISC-V emulator. So what this does is it's actually emulating a RISC-V processor. It's basically simulating one. And what this will allow you to do is actually kind of investigate every instruction that we're going to talk about and how it interacts with a general architecture, a general RISC-V architecture. So what is this thing? This looks like a lot, right? So when you click on the link in Canvas, it will bring you directly here. So you're staring at a lot of stuff here. So let's break it down. On the left here, you have your program memory. Now your program memory is actually going to be stored in binary. Okay, so everything, remember, goes back to binary. This is where your program is stored, and on the left here you get to see the binary or the hex representation of the actual program, the code that it's running, the specific instruction that it's running. On the right here, you get to tell what format you want it. You can put it in instruction mode, you can put it in decimal mode if you want to convert it to different things. We'll talk about that in a little bit. But keep it in instruction mode for now. There are a ton of examples on this website. When you preload it, it starts out with Hello World, but there's a lot of other cool stuff that lets you do certain things that are a little bit more complicated. So what is this thing? What is it doing for us? So it being an emulator, what it'll do is actually run the code for us and let us see how it works. So by default, if you don't change anything right now and you hit run, if you look at it, it just created this bitmap output. Cool, so it just made some colors and stuff. Ooh. I mean, it is cool. Don't get me wrong. We'll talk a little bit more about like displays and stuff like that. But for now, if you notice, if I run this thing, right, so this one should print hello. If you notice, this thing's actually stopped, is in a loop right now. It's actually running the code. So if I hit reset, I can add a breakpoint wherever I want. So let's say I wanted to investigate more specifically this add immediate command, right? So what I can do is if I click that dot and I hit run, it'll basically run everything up to that point. Now what'll happen is it'll actually set up everything in terms of what's happening in your program memory and stuff like that, and it allows you to kind of step forward and investigate certain things. So that's okay. That's cool, but the real power in this is, let me reset again, and let me make sure I'm on the hello example. I personally find it more powerful. One of the more powerful things to do is step. So you can say, I want to run this one step at a time. So if I step this, look what happens. So it runs the line of code that's currently highlighted. So let me reset that again. When I hit step, you're going to see you saw a lot of stuff turn orange. That is all the things that have changed. Note that right now, a lot of these blocks, like our ALU, which is our kind of our data manipulation circuit, what we kept calling that, you know, it's not set to anything. The comparator is not set to anything. Nothing's set up. The program counter is pointing at 0. This thing is purely reset. When I try to run the first instruction, all of a sudden now everything changes. We have changes in the general purpose registers. We have the ALU is now set to add. We have different inputs in here now. We have a result and we're storing it somewhere. And these arrows are meaningful. It actually shows you where certain things are coming from. And if you look at that, the program counter was incremented. And this instruction register, which we've not really talked about yet in class, actually picks apart this thing and kind of determines. It's part of that control circuit, really. It determines what should be happening and what needs to be determined where and what pins and bits need to be set. So it's all this really cool thing. And you can step through every line of code here and see what it's doing. So right away, that's a really powerful thing and a great way to kind of check your understanding of what these instructions are doing. But it gets even better than that. So I'm going to reset again. Again, that's like hitting the reset button on our processor. There's this little checkbox up here called animation. So what that will do is it actually animates the process of this instruction being decoded, getting things set to the right places, things happening and loading. It's insane how much work got put into this. So ready? If I want to run this instruction here, this add I x1 x0 32, right? If I want to run that, what you can do is you can hit step. You can also hit run, but you can hit step, and if you look at what happens, all of a sudden, wow, we get to see like the program counter gets pointed in, and we want to point to this instruction, and it gets pulled into the instruction register, decoded, tells the ALU what to do, what registers to pull from, where to throw the results, what to do at the end of the program counter. You actually get to see the flow here, and you can control the speed here. If you want it to go a little bit slower or a little bit faster, you can set the speed of this thing so you can actually follow this thing through. The higher the speed, the faster it'll go. So if you wanted to say, look at this thing, you do have to wait for these instructions to be done and completed before you move to the next one. So if I wanted to like step through the add immediate, which was basically saying take the contents in x0, add 32 to it, decimal 32 to it, and then throw the results in x1. Well, if I want to step through that, it pulls the program counter and it says, hey, program counter, where am I at? And it says, you're at the beginning, 0000. Pulls the data in from program memory, again, stored as binary, represented here in hex. And it says, okay, decompile it, or basically say, oh, look, it's an add immediate. What's my immediate value? Constant generator. Throws it in. It pulls in all the registers that it needs to, sets the ALU to be an add, throws the result into the general purpose register, and finally the program counter increments to 4. Now, if I wanted to say fast forward to this jump command to see how it runs, what you can do is, what I just did was uncheck the animation. Let me just set this back to its normal speed. So you can uncheck the animation, and now once you're there, by setting a breakpoint, you can click the animation, hit step, and you can see how this runs. So like a jump command, for example, is different than an add command, and you can actually see how it manipulates the program counter. So we're actually using the current value, and we are subtracting 16 from it. And if you look, we went from, let me reset run so I can explain this real quick. So what you're seeing is, reset, my bad, breakpoint, run, and then I want to do a step. So the big thing here, for example, this is where this is an amazing tool, is you get to see that the jump command manipulates the program counter. It pulls in the current value, finds your constant, subtracts it, takes the result, throws it back into the program counter, and now the program counter is ready to point you back somewhere in your code. It's really cool to help see what's happening here. Now, all of these things down here, the text I/O, the general purpose I/O, and all this other stuff, that's cool if you want to look at that stuff, but really from where we're at in the course, you can also custom type in things. So, spoiler for the homework, you can do a lot of stuff here. Remember how so this will take and basically set 32 into x1, right? In the beginning. Well, what if I wanted to, I don't know, let me clear things out here. You can customize your code here. You can literally type in whatever you want. So for example, what if I wanted to do our add command from a homework where it was literally take x1 and double it. Take x1, take the value from x1, add it to itself, and store it back into x1. And if you wanted to see how that worked, we can. So I hit reset. Let's step through the first one real quick. So again, our first thing is taking 32, getting the instruction register decodes what happens. We pull in a 0 register and 32. We store it back into x1. Awesome. Now we're ready to run the next instruction. So we move to instruction address number 4. It decodes our add, and if you look, it says, hey, look, we want to do an actual normal add, pulling from register 1 twice, add them together, take the result, throw it back. So it allows you to really kind of see what's happening here, because if you're coming from the world of high-level languages, it's sometimes kind of strange to see something like this add x1, x1, x1 and try to see what's happening to it. So this is a really amazing tool, and it gets even slicker because you can even go in here and change your format to decimal. Now you may think, wait a minute, why would I care about decimal, right? So if you have a calculator open, most of your either Mac or PC or Linux, they all have calculators that should have programming views. So you can go to View and hit Programmer. Here's what you can do. Take this decimal value, like the one that we were doing in class or from your homework, copy it, paste it, and note that you are in decimal value. So you hit base 10. And now it's a little hard to see, but take a look. If you compare this to your homework, that should be the same binary. And in these calculators too, you can actually manipulate the binary themselves and get a decimal value, and you can check things like that. So this tool is just an amazing resource for you all from a learning perspective. What doesn't this tool show you? Just as a disclaimer, what doesn't this tool show you? This tool doesn't show you the hardware that's required to run it. And that's where we're going to start our discussion next lecture, is saying, okay, this allows us to investigate the functionality that we want and what these things should be doing. Let's build the hardware that'll actually run this thing. So with that, try this out. I highly recommend that you take some of the problems from the homework, throw them in here. You can either type them in an assembly style where it looks like this. You can type it in as a decimal, which again, I recommend trying to do that. So if you have it in binary, use that calculator. Be careful of your Indianness is what I will say. So what I mean by that is, I don't know why I closed the calculator. Let me show you what I mean by Indianness. So look, see this memory here? This is your least significant byte, 93. The most significant byte is 2. So what I'm trying to get at is that if I copy this, put it into my calculator, and paste it as decimal, and I convert it to hex, what you're going to see is that you have to be careful of the order here. And we'll talk about it more in class about why you would pick what sort of Indianness and things like that. But just be careful because look, this 93 is actually at the end here. It's what we would typically show the least significant bit. We just typically read things the other way. So with that, this is, again, an amazing, amazing, amazing tool. I can't recommend enough that you take time today and over the next couple days and just try this thing out.